So today we're going to be doing May-June 2023 paper 11. Question number 1 says element X has 6 more protons than element Y. Which statement must be correct? So the first statement says atoms of element Y are smaller than atoms of element X. So X has 6 more protons than Y. X has 6 more protons than Y. Now let's say that they were in the same period. So let's take something like lithium versus fluorine. Right? If we took lithium versus fluorine, fluorine is actually smaller. Fluorine is actually smaller, right? So fluorine would be X, it has 6 more protons, and Y would be lithium. So in that case, Y is actually bigger, right? It doesn't have to be smaller. Okay, it doesn't have to be smaller. Okay, so statement A is incorrect. Okay, statement A is incorrect. Now, statement B says element X has a full shell of electrons. So over here, B is the answer. The reason why is because again, element X has 6 more protons than element Y. Right, now let's say element Y was hydrogen. If element Y was hydrogen, then element X would be 6 more protons. So that would be 1 plus 6, so that's 7. That would be nitrogen. Right? Nitrogen does have a full shell of electrons. Right? Nitrogen has one full shell of electrons. That's the first shell. Right? So the question is saying that it has to be at least one full shell of electrons. There has to be a full shell of electrons, means there has to be one full shell at the very least. Right? And since element X has 6 more protons, no matter what element Y is, right, even if element Y was hydrogen, that's the only element that doesn't have a full shell of electrons. Hydrogen is the only element that doesn't have a full shell of electrons. Any other element will always have one full shell of electrons. Helium, first shell is full, and then second period onwards, obviously the first shell is full and then the second shell is being filled up, right? Which means that statement B must be correct. Okay, statement B must be correct. Which statement explains why calcium has a higher melting point than barium? Now, calcium is higher up in the group, right? Barium is further down in the group. And because the cations become larger, okay, because cations become larger, right, the charge density decreases, okay? So the ionic radius, okay, the ionic radius increases, right? So the size of the cations increases, which means that the charge density decreases, okay? And because the charge density decreases, we have weaker metallic bonds down the group. Okay, we have a weaker attraction between the ions and the delocalized electrons. Okay, so calcium cations are smaller, right? Because calcium cations are smaller, they have a stronger attraction to the delocalized electrons. Yes, okay, so statement A is correct. Because they're smaller, they have a greater charge density, which means they have stronger attractions between the cations and delocalized electrons. 3 statements about potassium and chlorine and their ions are listed. So the ion for potassium is K+, the ion for chlorine is Cl-. Which statements are correct? So the first statement says the atomic radius of a potassium atom is greater than the atomic radius of a chlorine atom. Now potassium atom is argon and then 4s1, right? It's 4s1. And a chlorine atom, right? A chlorine atom is neon and then 3s2, 3p5. So again, potassium has 19 electrons. The potassium atom has 19 electrons. So that's argon, that's 18 plus 1, 19. And chlorine has 17. So that's 10 plus 7, right? So that's 17. So potassium has 4 shells. So that means that the atomic radius of potassium must be greater, right? The atomic radius of potassium is greater. It has more shells. Statement 2 is incorrect. The first ionization energy of potassium is much lower. Okay, is much lower. Remember, group 1 elements have a much lower ionization energy and potassium has an additional shell, right? Potassium has an additional shell, right? So there's 2 things here. First of all, if you guys remember the trends for ionization energy, right? We have this sort of increasing trend across the period, right? So if you looked at period 3, this would be sodium and then this would be chlorine, right? And somewhere over here, okay, this would be chlorine. So across the period, as the nuclear charge increases, number of shells and shielding remains the same, the attraction becomes stronger, so the first ionization energy increases, right? Attraction between the nucleus and valence electrons increases across the period. So group 1 elements have the lowest first ionization energy in their periods. And potassium would be even lower than sodium because potassium has an extra shell, so it comes in the next period. So this would be potassium, right? This would be potassium. It would be even lower than sodium. So statement 2 is incorrect. Okay, statement 2 is incorrect. And then the ionic radius of a potassium ion is greater than the ionic radius of a chloride ion. Now over here, Potassium ions are K plus, chloride ions are Cl minus. They both have 18 electrons, so they both have the configuration of argon. But because potassium has a greater proton number, greater nuclear charge, right? That means that the electrons are attracted more strongly to the nucleus. So potassium ions are actually smaller than chloride ions. Okay, potassium ions are smaller than chloride ions, right? They're the same configuration, same shielding, same number of shells, right? Everything about their electronic structure is the same. Greater number of protons means stronger attraction, right, towards the valence electrons, which means a smaller radius. So the answer is A. Okay, only statement 1 is correct. Statement 3 is also incorrect. For which equilibrium do both of the equilibrium constants Kc and Kp have no units? For that, the answer would just be A, right? For Kc, we have to look at the concentration of the reactants, right, squared in this case because Hi to the power of 2, right, because that's the stoichiometric coefficient, divided by hydrogen times iodine to the power of 1, right, because that's the stoichiometric coefficient here. So we have concentration squared in the numerator, we have concentration times concentration in the denominator. So Kc is unitless, okay, and then Kp is also unitless, right? Kp is just the partial pressure of Hi squared, okay, the partial pressure of Hi squared divided by the partial pressure of hydrogen times the partial pressure of iodine. So here in the denominator we have pressure squared, right? Pressure times pressure. In the numerator we have pressure squared. So Kp is unitless and Kc is unitless. So the answer is A. What you guys should remember is that for Kc, right, we can have gases or liquids or something in aqueous solution, right? Concentration. For concentration, we can never have solids in either of these expressions. We can never have solids in either of these expressions. For Kp, we must have only gases in the expression. Okay, we must have only gases in the expression. In this case, if you notice, all the equilibriums have just gases. So we just have to see where the powers cancel each other out, okay, in the numerator and the denominator. So the answer is A. Calcium carbide reacts with water as shown. The data below the equation show in kilojoules per mole the standard enthalpies of formation of the compounds involved. What is the standard enthalpy change of the reaction shown? Now, if they've given you enthalpy change of formation data, right? So if they've given you the enthalpy change of formation data for the reactants and the products of a particular reaction, you can find the enthalpy change of the reaction by finding the enthalpy changes of formation of the products and subtracting the enthalpy changes of formation of the reactants, right? So here in our products, we have calcium oxide, we have minus 635 for calcium oxide. So that's one of the products, minus 635 plus 228, right? That's C2H2, so plus 228. And then we subtract the enthalpy changes of formation of the reactant. We're going to subtract minus 286, so minus 286, and we subtract negative 60, so minus 60. And that comes out to negative 61. So the answer is B. Question number 6 says in the sodium chloride lattice, the number of chloride ions that surround each sodium ion is called the coordination number of the sodium ions. What are the coordination numbers of the sodium and chloride ions in the sodium chloride lattice? You guys should remember that each sodium ion is surrounded by 6 chloride ions and each chloride ion is surrounded by 6 sodium ions. So the coordination number for both of them is 6. Histidine is an amino acid. What are the approximate bond angles 1, 2, and 3? Now over here we have a carbon that's bonded to 3 atoms, right? We have a carbon that's bonded to 3 atoms. So over here there's no lone pairs, right? Because all 4 of carbon's valence electrons are bonded, right? There's 3 atoms, so it has a trigonal planar geometry, so the bond angle is 120 degrees. So bond angle 1 is 120 degrees. Bond angle 2, we have a nitrogen making 3 single bonds. We know that nitrogen has 5 valence electrons, so it has a lone pair, right, making 3 single bonds. So 3 of its electrons are bonded, 2 of them are left, so that's a lone pair. We have a lone pair and 3 atoms bonded to the nitrogen. That means it has a trigonal pyramidal geometry. So this bond angle is 107 degrees, okay, similar to ammonia. And then that means that the answer must be B, right? And bond angle 3 is 109.5, right? Carbon is making 4 bonds, so that's a tetrahedral geometry, so that's 109.5 degrees. The contact process takes place at a pressure between 100,000 pascals and 200,000 pascals. A catalyst is used. Which statement is correct? A catalyst is added to increase the yield of the reaction. That's incorrect. Catalyst does not affect the yield, it only affects the rate. Changes in pressure have no effect on the position of equilibrium. That is incorrect as well, because if you guys remember the equation for the contact process, right? This is the equation. SO2 reacts with O2 to give you SO3, right? And over here we have 3 moles of gas on the left hand side and we have 2 moles of gas on the right hand side. So we have an unequal number of moles of gas. So an increase in pressure will favor the right hand side, it will favor the side with fewer moles of gas. So B is incorrect. The equilibrium yield of the reaction is very high under the conditions used. So statement C is correct. Okay, statement C is correct. D is incorrect because the catalyst being used is vanadium 5 oxide. So just by elimination, we know that statement C must be correct. Just be aware that the contact process is a relatively high yield, okay, whereas the Haber process has a much lower yield. The Haber process, which is used to manufacture ammonia, right, when nitrogen and hydrogen react to form ammonia, right, that's where we use this iron catalyst, okay, that has a much lower yield. Bromine reacts with aqueous sodium hydroxide at 25 degrees Celsius. This is the reaction shown. This is very similar to the reaction of chlorine with sodium hydroxide. The NaOBr formed is unstable at 25 degrees Celsius and reacts further. Which reactions are disproportionations? Now, in the first reaction, the initial oxidation state of bromine is 0. In sodium bromide, bromine is -1. And in NaOBr, bromine is +1, right? Again, sodium is +1, oxygen is -2. So we have +1, -2, that's -1. That means bromine must be +1, right? +1 -2 is -1. Bromine must be +1. So bromine is going from 0 to -1 and +1, starting with the single oxidation stage being reduced and oxidized simultaneously, right? That's what disproportionation is. So reaction 1 is the disproportionation, and then reaction 2, bromine is +1 initially, and it goes to -1 here, and it goes to +5 over here. Okay, again, we know it's +5 because sodium is +1. Okay, sodium is +1. We have 3 oxygens, which are -2 each. Our bromine is X, this is equal to 0, X is equal to +5. Okay, so again, bromine is undergoing oxidation and reduction simultaneously. Okay, it's being oxidized from +1 to +5 and being reduced from +1 to -1. So the answer is A. Okay, both reaction 1 and reaction 2 are disproportionation reactions. Which statement is correct? The relative atomic mass of a chlorine 35 atom is 35.5. No, that is incorrect. Okay, this is a particular isotope, so we would take the relative isotopic mass of a chlorine 35. Okay, so that's incorrect. This is the average mass of the different isotopes, not the mass of a specific isotope. The relative formula mass of calcium carbonate is 100.1. That is correct. Okay, you can just check from the periodic table. Calcium is 40.1, carbon is 12, and we have 3 oxygens. That's 3 times 16, and that gives you 100.1. So the answer is B. Iodine and propanone react according to the following equation. If the concentration of propanone is increased, keeping the total reaction volume constant, okay, the initial rate of the reaction also increases. What could be the reason for this? So you're increasing the concentration of propanone. When we increase the concentration, right, our volume is fixed, okay, our volume is fixed. What we've done is we've increased the number of particles, right? If you have more particles, you have more collisions taking place per unit time. So the frequency of collisions increases and therefore the reaction rate increases, right? So the frequency of successful collisions increases as a result of the frequency of collisions increasing. Note that A is incorrect. Not a greater proportion of collisions are successful. This would mean that a greater percentage of the collisions are successful. That's not true. So for example, right, what you would have here is, let's say you had 100 collisions per second and 2% of them were successful, you get 2 successful collisions. Now let's say we have 200 collisions per second. Now we have 4 successful collisions. The proportion of collisions that are successful is still 2%. The proportion of collisions that's successful is still 2%. The same fraction of collisions are successful. But because we have more collisions, right, the rate increases. If you want a greater proportion of successful collisions, okay, if you want a greater proportion of successful collisions, you can either add a catalyst that will lower the activation energy, or we can increase the temperature. That will mean that the average energy of the particles is greater. In that case, a greater proportion of collisions would be successful. Four successive ionization energies of element E are shown. Element E is in period 3 of the periodic table. In which group of the periodic table is E? Now over here, we don't really see any big jump, right? From the 5th to the 6th, from the 6th to the 7th, or from the 7th to the 8th, right? We don't see any big jump from the 5th to the 6th, so that means it's not group 15, right? Group 15 would mean 5 valence electrons, so that means you would see a big jump from the 5th to the 6th. Group 16 would mean you see a big jump from the 6th to the 7th, because that would be 6 valence electrons. And a big jump from the 7th to the 8th would mean that it's group 17, because that would mean 7 valence electrons. The first 7 are easier to remove, the 8th one would be much more difficult. That would mean 7 valence electrons. Because you're not seeing any big jump in each of these cases, we know it's not 15, 16, or 17, so it must be group 14. Okay, so this is another example in which you have to find the answer by elimination, because there's no information given to you here that would directly lead you to conclude that group 14 is the answer. In this question, you should assume that the gas formed behaves as an ideal gas. A 1.7 gram sample of magnesium reacts with 50 cm cube of 2.2 mole per dm cube HCl at 303 Kelvin and 110,400 pascals. Which volume of gas is produced measured under these conditions? So we've been given the mass of magnesium and we've been given the concentration and volume of HCl. You know, magnesium and HCl react to form the chloride and hydrogen gas. So we have Mg plus HCl gives us MgCl2 plus hydrogen gas. Okay, and 1 mole of Mg reacts with 2 moles of HCl. Number of moles of magnesium is the mass divided by the molar mass, which is 24.3, which is 0.07 moles. And the number of moles of HCl is concentration times volume. The concentration is 2.2. The volume is 50 cm cube, so 50 divided by 1000. And this comes out to 0.11 moles. 0.11 moles. So over here we know that magnesium is an excess. Magnesium is an excess because if we have 0.07 moles of magnesium, it's going to react with 0.14 moles of HCl, right? Because 1 mole of magnesium reacts with 2 moles of HCl. So if we have 0.07 moles of magnesium, we need double the number of moles of HCl. We don't have enough HCl to react with all the magnesium. So that means that HCl is the limiting reactant. Okay, HCl is the limiting reactant. So this is the limiting reactant, which means that the number of moles of hydrogen gas produced, is equal to 0.11, that's the number of moles of HCl that are going to react, divided by 2. Okay, we're going to take the limiting reactant to find out how much hydrogen gas is produced. So we get 0.055 moles of hydrogen gas. So we have 0.055 moles of hydrogen gas, and now we need to find the volume of hydrogen gas in decimeter cube. Okay, we're going to use PV is equal to nRT. PV is equal to nRT. We rearrange for the volume, so volume is nRT over P. The number of moles is 0.055, R is 8.31. The pressure is in pascals, right? We have to take SI units in this expression, and the temperature is 303. So this comes out to 0.0013 meter cube. Okay, this comes out to 0.0013 meter cube. To convert to decimeter cube, we just multiply by 1000, and that gives us 1.3 decimeter cube. Chlorine dioxide reacts with aqueous sodium hydroxide to produce water and a mixture of two sodium salts, NaClO2 and NaClO3. What is the mole ratio of NaClO2 to NaClO3 in the product mixture? So here ClO2, right, ClO2 is being converted to ClO2 minus and ClO3 minus. Okay, ClO2 minus and ClO3 minus, right? Because again, Na is 1 plus. Now the initial oxidation state of chlorine is plus 4, right? Because the two oxygens are minus 2, chlorine is plus 4. In ClO2 minus, chlorine is plus 3, right? Chlorine is plus 3. Why? Because the two oxygens are minus 4. The two oxygens are minus 4. So the chlorine must be plus 3, right? Because plus 3 minus 4 gives us minus 1. And in ClO3 minus, chlorine has an oxidation state of plus 5, right? That's the chlorate 5 ion. So chlorine is being oxidized from plus 4 to plus 5, and it's being reduced from plus 4 to plus 3. When it's being reduced, the change in oxidation number is minus 1, is decreasing by 1, right? Going from plus 4 to plus 3. And it's being oxidized, the change in oxidation state is plus 1, right? Going from plus 4 to plus 5. So the changes in oxidation state are already balanced here. The changes in oxidation state are already balanced, which means that ClO2 minus and ClO3 minus are being produced in a 1-to-1 ratio. Remember, the changes in oxidation state have to be balanced for the equation to be balanced. The temperature of a sample of an inert gas is increased. What effect does this have on the number of molecules with the most probable energy and on the number of molecules with higher energy? Now this is about the Boltzmann distribution, right? In the Boltzmann distribution, we have number of molecules on the y-axis, we have energy on the x-axis, so we have number of molecules here, right? This is the Boltzmann distribution for, let's say, a particular temperature T1. If you increase the temperature, the curve shifts to the right. Okay, the curve shifts to the right like this. Now you have more particles at a higher energy, right? You have more particles at a higher energy. Again, the area under the curve gives you the number of molecules. So you have more particles at a higher energy, obviously, right? Because if you increase the temperature, the kinetic energy of the particles is greater, right? So you have more molecules at a higher energy. Number of molecules with higher energy increases. Now the most probable energy is the energy at which we have the greatest number of molecules. Okay, it's the energy at which we have the greatest number of molecules, right? So at this energy, right, the number of molecules here is this, right? And when the temperature is increased, the number of molecules with the most probable energy decreases, right? When the temperature is increased, the number of molecules at that modal energy, okay, at that modal energy, again, the modal energy is the energy where we have the greatest number of molecules. So the modal energy, in other words, the peak, right? The peak is actually lower. So the number of molecules with the most probable energy decreases, which means that the answer is B. For which compound is there the greatest percentage loss of mass on strong heating? Now over here, when we talk about the decomposition of group 2 carbonates, the carbonates decompose to form the oxide and carbon dioxide, and the nitrates decompose to form the oxide, nitrogen dioxide, and oxygen gas. Now, without doing any calculation, we know that there's a much greater loss in mass when a nitrate decomposes. There's a much greater loss in mass when a nitrate decomposes. So it can't be the carbonate, right? There's a greater loss in mass when the nitrate decomposes as a percentage of the initial mass. And now the percentage loss in mass, okay, the percentage loss in mass, okay, will be the mass of gas divided by the mass of the initial solid, right? The mass of the initial solid. Now, because magnesium nitrate has a lower MR, right? It has a lower MR. That means that it has a lower mass per mole. It has a lower mass per mole. And because it has a lower mass per mole, the percentage loss in mass will be greater. Because in the case of calcium nitrate and magnesium nitrate, the same mass of gas will be lost per mole, right? The same mass of gas will be lost per mole. But because the mass of magnesium nitrate is lower, the denominator is smaller, that means that the percentage loss in mass would be greater for anhydrous magnesium nitrate. The solids sodium chloride and sodium iodide both react with concentrated sulfuric acid at room temperature. With sodium chloride, the products are NaHSO4 and HCl, whereas with sodium iodide, the products are NaHSO4, HI, iodine, SO2, H2O, S, and H2S. What is the explanation for the difference in products? Now, the reason why we have so many different products with iodide is because iodide is a much stronger reducing agent than chloride, right? Down the group, the reducing strength of the halides increases. The reducing strength of the halides increases, right? They're stronger reducing agents down the group. Reducing agents undergo oxidation. So their ability to reduce something else and undergo oxidation, that means their ability to lose electrons increases, right? Because the number of shells increases, shielding increases, the attraction between the valence electron and the nucleus decreases. So it's easier for them to lose electrons, undergo oxidation, and reduce something else. So iodide reduces sulfuric acid, whereas chloride does not reduce sulfuric acid. So the answer is just C. Okay, iodide ions are better reducing agents than chloride ions. SiO2 has a melting point of 1713 degrees Celsius. It reacts with hot aqueous sodium hydroxide to form sodium silicate and water. No reaction occurs when SiO2 is added to hot sulfuric acid? What can be deduced from this information? So SiO2 reacts with hot alkali but not with hot acid. That means SiO2 must be acidic. SiO2 must be acidic because it's reacting with hot alkali, but it does not react with acid. It's not amphoteric because amphoteric means it reacts with both alkali and acid. And we know that SiO2 has a giant covalent structure, right? And the evidence given to us is that it has a very high melting point. So the answer is C. Okay. Element X has the second largest atomic radius in its period. An atom of X has 3 occupied electron shells only. The oxide of X is shaken with water. What could be the pH of the resulting solution? Now the atomic radius decreases across the period. It decreases across the period. So in a given period, the largest atomic radius will be group 1 followed by group 2. So if it's second largest atomic radius, that would be a group 2 element. And if it has 3 occupied shells, it means that it's in period 3. Okay, it means that it's in period 3. So in group 2 and period 3, we have magnesium. So the oxide of magnesium is magnesium oxide. And we know that magnesium oxide is partially soluble in water, right? It's considered to be insoluble or very partially soluble. So because it's partially soluble, it forms a slightly alkaline solution. Now again, it is a strong base. It is a strong base, but because it's not very soluble, right? Because it's not very soluble, right? The pH is not very high. Okay, the concentration of hydroxide ions in solution is relatively low. Okay, so again, magnesium oxide dissolves partially, okay, or very slightly in water to form magnesium hydroxide, which gives us a slightly alkaline solution. Which emission from an internal combustion engine contributes to the erosion of marble statues? This would mean what contributes to acid rain. Okay, that's what the question is asking. So we know that nitrogen dioxide contributes to acid rain. The diagram shows the melting points of 8 elements with consecutive atomic numbers. Which element could be sodium? Now across the period, we know that the highest melting points are for the group 14 elements, right? That would be silicon or carbon. In this case, that would be silicon, right? Because it has a macromolecular structure. Below that, we would have aluminum. Before that, we would have magnesium. And before that, we would have sodium. So here the answer is C, okay? C is your group 1 metal. And then before that, we have neon, right? Which is a noble gas. So it has a very, very low melting point. The boiling points of Br2, ICl, and IBr are given in the table. Which row explains why the boiling point of ICl is greater than Br2 and why the boiling point of IBr is greater than ICl? Now I'll mention here that chlorine has atomic number 17, bromine has atomic number 35, and iodine has atomic number 53. Okay, so a molecule of Br2 has 70 electrons and a molecule of ICl has 53 plus 17, that's also 70 electrons. So Br2 is 35 times 270 electrons and ICl has the same number of electrons. So they have the same number of electrons, but ICl is a polar molecule because chlorine is more electronegative than iodine, right? Down the group electronegativity decreases. So the reason why ICl is greater than bromine is because ICl has intermolecular forces due to permanent dipoles. Okay, ICl has permanent dipoles. So the answer has to be B or D. Now in the case of ICl and IBr, right, IBr simply has more electrons, right? IBr has 53 plus 35, so it has 88 electrons. Now, the IBr bond is actually less polar. Okay, the IBr bond is less polar. So ICl is a more polar molecule, but despite that, IBr has a greater boiling point. Despite that, despite being less polar, it has stronger intermolecular forces. And the reason why is because it has a greater number of electrons. And because it has a greater number of electrons, it has stronger instantaneous dipole-induced dipoles. It doesn't have stronger permanent dipoles because it's less polar. The difference in electronegativity between iodine and bromine is smaller. The difference between iodine and chlorine is greater. So the answer has to be B. A solution contains both magnesium and strontium ions at the same concentration. The solution is divided into 2 equal portions. Aqueous sodium hydroxide is added dropwise to one portion. Dilute sulfuric acid is added dropwise to another portion. The sodium hydroxide provides hydroxide ions and the sulfuric acid provides sulfate ions. Which precipitate is seen first with NaOH and with sulfuric acid? Solubility of hydroxides increases down the group. So magnesium hydroxide is less soluble. So that's the precipitate we're going to see first. And the solubility of the sulfates decreases down the group. So that means that strontium, which is lower down in the group, will be less soluble. Okay. So sulfate down the group less soluble. Okay. Hydroxide down the group is more soluble. So strontium hydroxide will be more soluble. Magnesium hydroxide will be less soluble. And then down the group, sulfates will be less soluble. So strontium sulfate will be less soluble. So the answer is B. Structural isomerism and stereoisomerism should be considered when answering this question. If a molecule contains two non-identical chiral carbon atoms, 4 optical isomers exist. How many isomers are there with the molecular formula C7H14O, a 5-membered ring, and a tertiary alcohol group? So the first thing we're going to do is we're going to draw out the structural isomers. Okay, we're going to draw the structural isomers that fulfill these requirements. We have a 5-membered ring. Okay, we have a 5-membered ring. We have a tertiary alcohol group. Okay, so that means that the alcohol group must be on the same carbon as a methyl group, right? The alcohol group has to be on the same carbon as a methyl group because the carbon with the OH must be bonded to 3 carbons. So now we have 6 carbons. We have 5 plus 1, 6, and now we need a 7th carbon, right? Now the 7th carbon can be over here, right? Another possibility is if we had this 5-membered ring, we had the OH group here, right? Again, the tertiary alcohol group has to be there, but instead of the methyl group being on the carbon next to the OH group, it can be the one over here, right? And then if you put it here, if you put it over here, right, it's the same as putting it over here, and putting it over here is the same as putting it over here, right? So again, alcohol is on carbon 1, so the methyl can either be on carbon 2 or it can be on carbon 3, right? So now we have 2 structural isomers. The third possibility is that we don't have a methyl group, but we have an ethyl group instead. So we can have an OH group and then an ethyl group, right? Now we have 7 carbons again. Now we have 7 carbons again. So here we have 3 different structural isomers. Okay, we have 3 different structural isomers. Now we have to consider the number of optical isomers. Now in the first case, we have 2 chiral centers. We have a chiral center here, right? Because this carbon is bonded to an OH, is bonded to a methyl. And if you notice, right, this molecule is asymmetric with respect to this carbon atom. And similarly, this carbon is also a chiral center. This carbon is also a chiral center, right? Because again, we don't have a line of symmetry here, right? This carbon is bonded to a hydrogen, a methyl, and then if I draw this line over here, right, we see that it's asymmetric. This group is different from this group. Okay, so we have 2 chiral centers here. That means that this particular structure actually represents 4 different optical isomers. It represents 4 different optical isomers. That's 2 to the power of 2, right? 2 to the power of the number of chiral centers. And then in the second structural isomer, again we have 2 chiral centers, okay, and the idea is the same. We have asymmetry around this carbon and it's asymmetric with respect to this carbon. So each of these carbons is bonded to 4 different atoms or groups of atoms. So again we have 4 isomers here, right? 4 optical isomers. So this structure represents 4 optical isomers. And here we don't have any chiral centers. The reason why is because if you notice, we have a line of symmetry with respect to this carbon atom here, right? We have a line of symmetry over here, so there's no chiral centers here, right? These are all CH2, so they're obviously not chiral centers. And then if you notice, the ring looks exactly the same if we go clockwise or counterclockwise. Okay, so this particular structure represents just 1 isomer. So the answer is 4 plus 4 plus 1, which is 9. Which reagent will react with pentanthreol to give a mixture of stereoisomers? So pentanthreol is we have a 5-carbon chain. We have an OH on the middle carbon. If we react with acidified potassium dichromate, we just get pentanthreone, right? This will become a ketone. This will become a C double bond O. It will become pentanthreone. We don't get a mixture of stereoisomers. So it's not A. If we react with concentrated sulfuric acid, we have elimination take place. The OH is removed and a hydrogen from the neighboring carbon is removed. Doesn't matter if it's this one or this one because it's symmetric. And what we end up getting We remove the OH and we remove the hydrogen from the neighboring carbon, and we end up getting a double bond. Now, what I've shown here is trans-pentuene. We can also get cis-pentuene, right? We can also get cis-pentuene. So when pentan 3-ol is dehydrated, right, concentrated sulfuric acid is used to dehydrate an alcohol. That's elimination of H2O, right? That's the mechanism, elimination, right? We remove an OH and hydrogen from the neighboring carbon. We get a double bond here. We get pentuene, but pentuene displays cis-trans isomerism. So the answer is B. Okay, we get a mixture of stereoisomers. An organic molecule W contains 3 carbon atoms. It requires 4.5 moles of oxygen for complete combustion. What could W be? So if we start with propane, right? If we start with propane, we have C3H8, right? That's an alkane. We react with oxygen, we get 3CO2 and 4H2O, right? We get 3CO2 and 4H2O, right? Because we have 3 carbons here and we have 8 hydrogens. So that means we have 3 times 2, that's 6, plus 4, that's 10 oxygen. So that would be 5 O2, right? We need 4.5 moles of O2. So A is incorrect, right? Now, the answer over here would be D. Okay, the answer over here would be D. The reason why is because D has an additional oxygen, right? We have C3H8O, which means we need one less oxygen atom over here for it to balance, right? Because we still have 3CO2 and 4H2O. Because we have one oxygen here, we need a total of 10. We would need 4.5 O2. Okay, we would need 4.5 O2. So the answer is D. The way I was able to deduce that was we know that propane needs 5 moles of O2. We know that propane needs 5 moles of O2, right? So that's almost equal to what we want, right? We want just half a mole lesser. We want just half a mole lesser. That means we want one more oxygen atom here. If we have one more oxygen atom here, right, we're going to need one less oxygen atom here. Again, because we know that we have C3H8, so we'll have 3 CO2 and 4 H2O. We'll have 10 oxygen atoms in total, right? So we want 10 on the left hand side, and in the case of propane we get 10 from here and 0 from here. In the case of propane 1-ol we get 1 from here, that means we get 9 from here, so that would be 4.5 O2. Of course, you could just figure out the molecular formula for each of these and go through each individual option as well, okay, and you'd find that the answer is D. Which equation represents a reaction that proceeds through initiation, propagation, and termination? This is free radical substitution. Okay, this is free radical substitution. So which of these reactions proceeds through a free radical substitution mechanism? Well, that would be the halogenation of an alkane, right? In this case, that's the chlorination of butane, right? When a halogen substitutes for a hydrogen, and a halogen substitutes for a hydrogen on a saturated carbon atom. So the answer is A. The essential condition, of course, is UV light for this reaction. Structural isomerism and stereoisomerism should be considered when answering this question. A set of isomeric hydrocarbons all contain 14.3% biomass of hydrogen. All react with bromine by addition, that means they all have a carbon-carbon double bond. 0.28 grams of each hydrocarbon react with 0.799 grams of bromine. What is the maximum number of isomeric compounds in the set? In other words, we first need to find the molecular formula of the hydrocarbon. We need to first find the molecular formula of the hydrocarbon and then figure out how many possible isomers are there for that particular hydrocarbon. So to find the empirical formula, right, they've given us the percentage by mass of hydrogen. So we know that the percentage by mass of hydrogen is 14.3%, right? So if we had 100 grams, hydrogen would be 14.3%, and then carbon would of course be 85.7%, right? That's 100 minus 14.3. So that means the number of moles we can find, right, for each of them by dividing by the atomic mass. That would be 85.7 divided by 12 for carbon, 14.3 divided by 1 for hydrogen. So we get 14.3, and we get 7.14 when we do 85.7 divided by 12. So the carbon to hydrogen molar ratio is 7.14 to 14.3. If we divide by the smallest number, that would be divided by 7.14. We get a ratio of roughly 1:2. So the empirical formula is CH2. That means that we have one carbon-carbon double bond, right? We just have one carbon-carbon double bond. It's an alkene with just one carbon-carbon double bond, right? because alkenes with a single double bond have this empirical formula. Now that we know the empirical formula, right, we're going to use this information to find the molecular formula. Now we know we have an alkene, right? It has just one double bond, right? It has one double bond. So we know that 1 mole of alkene reacts with 1 mole of bromine, right? To give us the product, right? 1 mole of alkene is reacting with 1 mole of bromine. Again, the reason we know 1 mole of alkene reacts with 1 mole of bromine is because we know that the alkene just has one double bond. One double bond reacts with one bromine molecule. We can find the number of moles of bromine. That would be the mass divided by the molar mass of bromine. The mass of bromine is 0.799. The molar mass for Br2 is 79.9 times 2. That's the atomic mass of bromine times 2. So that's 159.8. And that gives us 0.005 moles of bromine, which means we have the same number of moles of alkene. We have 0.005 moles of alkene. Now that we have the moles of alkene, we can find the MR of the alkene. The reason we're finding the MR is so that we can find the molecular formula. The MR is just the mass divided by the number of moles. So that would be 0.28 divided by 0.005. And that gives us the MR of the alkene as 56. Okay, so the MR of the alkene comes out to 56. Right? Now CH2 has a mass of 14. CH2 has a mass of 14. The actual alkene has an MR that's 4 times the empirical mass. The empirical mass is 14 and the MR is 4 times that. So the actual alkene would have a molecular formula C4H8. So now the question is how many alkenes have the molecular formula C4H8? Now for this, we'll have to consider structural and stereoisomers. So first we look at structural isomers. We know there's 3 types of structural isomers: functional, chain, and position. We won't have functional here because they're all alkenes. So it will be chain and position. So we go chain by chain. In a straight chain, right, in a straight chain for C4H8, right, we can have but1ene, right? We can have but2ene, but but2ene exhibits cis-trans isomerism. We can have cis or trans but2ene. So these are all the straight chain possibilities: but1ene, trans but2ene, and cis but2ene. And then of course we can have branching as well. So we have a 3-carbon chain with a branch, and there's only one possibility with that, that's methylpropane. So we have 4 different alkenes with the molecular formula C4H8. So the answer is C. Which row describes the solvent used and the type of reaction occurring when bromoethane reacts with sodium hydroxide to form ethene? So when bromoethane, that's a 2-carbon halogenoalkane, is reacting to form ethene, that's an alkene. So that's the elimination of halogenoalkanes. For this we use NaOH in ethanol. Okay, we use NaOH in ethanol. So the solvent is ethanol and the type of reaction is elimination. So the answer is A. If you want to replace the bromine with an OH to make an alcohol, we use aqueous sodium hydroxide instead of ethanolic sodium hydroxide. Which row describes the type of reaction that occurs when propan-1-ol reacts to form the named carbon-containing product? When propan-1-ol, so propan-1-ol is this guy, right? If it forms 1-chloropropane, you're just replacing the OH with the chlorine. You're replacing the OH with the chlorine. So it's not an addition reaction, it's a substitution reaction. Okay, so A is incorrect. Carbon monoxide does not form as a result of complete combustion. It forms as a result of incomplete combustion. Propene forms as a result of dehydration of propan-1-ol. This is correct, right? So the answer is C. Again, in dehydration, right, the mechanism is elimination. Okay, elimination of H2O, right, is a dehydration reaction. We remove the OH and a hydrogen from the neighboring carbon, and we end up with a double bond, and that gives us propene. Which statement describes what happens when 2-chloro-2-methylpropane is warmed with aqueous sodium hydroxide? We have propane, that's a 3-carbon chain. We have 2-chloro-2-methyl, so we have a chlorine and a methyl on the same carbon. This is a tertiary halogenoalkane. This is a tertiary halogenoalkane. That means the answer must be C or D, and tertiary halogenoalkanes react via an SN1 mechanism. Okay, so the answer is C. Okay, they react by an SN1 nucleophilic substitution mechanism, right? With aqueous sodium hydroxide, the hydroxide replaces the chlorine. The hydroxide substitutes for the chlorine and we end up getting an alcohol. The reason why tertiary halogenoalkanes favor the SN1 mechanism is because we form a tertiary carbocation intermediate, okay, which is relatively stable, requires a relatively low activation energy to form, okay, due to the positive inductive effect of the alkyl groups. How many structurally isomeric secondary alcohols are there with the molecular formula C5H12O? Now here we only want to consider structural isomers, okay, and we only want to consider secondary alcohols. So secondary alcohol means the carbon with the OH is bonded to two carbons. A carbon with the OH is bonded to two carbons and just one hydrogen. The carbon with the OH is bonded to two carbons and just one hydrogen, right? So we have a CHOH group. Okay. Now, since again we want to consider structural isomers, we think about the three types: functional, chain, and position. Obviously, we don't have any functional here because they're all alcohols. So it must be chain or position. So we start chain by chain. Okay, we go chain by chain, right? We go with a straight chain first. 5 carbon alcohol. Secondary alcohol means that it can be pentan 2-ol or pentan 3-ol. Okay. It can't be at the end, right? That would be pentan 1-ol. That's a primary alcohol because that would be a CH2OH. That would be a CH2OH. That would be a primary alcohol. So it can either be pentan 2-ol or it can be pentan 3-ol. Okay, or it can be pentan 3-ol. Again, we don't really care about stereoisomers here. So just structural isomers. So these are the straight chain possibilities, right? These are the possibilities of the 5 carbon chain. With a 4 carbon chain, right? With a 4 carbon chain, we have 4 carbons like this, right? And then we have a methyl group. So that's a 4 carbon chain. Now the OH group, if it was here, here, or here, right, on any of the ends, there would be a CH2OH. That would be a primary alcohol. If the OH was here, that would be a tertiary alcohol. So that's also not a valid position. So the only place that the OH can go is over here, right? This carbon is bonded to 2 carbons, so that's a secondary alcohol. So that's the only possibility with a 4 carbon chain. And then if you think about a 3 carbon chain, right, if you think about a 3 carbon chain, right, we get this, right? We have a 3 carbon chain with 2 methyl groups, and the OH can only go here, 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 or here. In each of those cases, that's a CH2OH. So the only possibility with a 3 carbon chain is going to be a primary alcohol. So it can't have a 3 carbon chain. So the answer is just C. There's 2 possibilities with a 5 carbon chain and 1 possibility with a 4 carbon chain. Which reagent can confirm the presence of a carbonyl group in an organic compound and does not distinguish between aldehydes and ketones? That is 2,4-DNPH, right? It's used as a test for carbonyl compound. It's a yellow solution that gives a bright orange precipitate with aldehydes and ketones, okay? But it does not differentiate between the two. Which compound gives a positive test with alkaline aqueous iodine and does not show optical isomerism? A positive test with alkaline aqueous iodine means that it has to be either a CH3CO group, okay, in an aldehyde or a ketone, or it has to be a CH3CHOH group. Okay, it has to be a CH3CHOH group. Okay. Now, if you look at option A, we have the CH3CO group present, right? We have the CH3CO group present, this ketone group, a methyl ketone, right? And this guy does not have a chiral center, does not show optical isomerism, means does not have a chiral center. This guy does not have a chiral center. So the answer is just A. Okay. B will just not give a positive test with alkaline aqueous iodine. C would give a positive test because you have that CH3CHOH group, but you have a chiral center here, right? You have a chiral center here. So that is not valid. We also have the CH3CO over here. We also have the CH3CO over here. So either one of these groups would give you a positive test. And then D again doesn't have any one of these two groups. Okay, it doesn't have either one of these two groups. So D would not give a positive result either. Two samples of compound X were treated separately with different reagents which were added in excess. The products of these two reactions are shown. Which reagents could be used for reaction 1 and reaction 2? Now in reaction 1, In reaction 1, right, what we're doing is we're oxidizing this aldehyde to a carboxyl group, right? We're oxidizing the CHO group to a CO2H group. However, the secondary alcohol is not being oxidized. The secondary alcohol is not being oxidized. So we're not going to use dichromate 6. We're not going to use hot acidified sodium dichromate 6 or potassium dichromate 6. The reason why is because sodium dichromate 6 will oxidize the secondary alcohol and the aldehyde. Okay, we have to use either Tollens reagent or Fellings reagent. Why? Because Tollens or Fellings will oxidize a CHO group only, right? They specifically oxidize CHO groups. There are tests for the CHO group. Okay, so since we only want to oxidize the aldehyde, we're going to use Tollens or Fellings. So the answer has to be C or D, right? Now Tollens is an alkaline solution, so we're going to make the salt of the acid, and then we're going to add H plus to get the carboxylic acid. And in reaction 2, we're simply reducing the aldehyde and the ketone, reducing this aldehyde and ketone to a primary alcohol and secondary alcohol group respectively. For that, we're going to use NaBH4. So the answer is D. Which method would produce butanoic acid? An acid-base reaction involving sodium butanoate. The answer is just A. That's correct, right? Because what we have here is we have this CH3, CH2, CH2, CO2 minus. If you just add acid, right, you get butanoic acid. You get CH3, CH2, CH2, and then CO2H. Okay, so this is an acid-base reaction. This butanoate is a base. It's a proton acceptor. We have an acid, right? So we have an acid-base reaction that gives you butanoic acid. B is incorrect because you have a 5-carbon nitrile here. If you hydrolyze this, you get pentanoic acid, not butanoic acid. Hydrolysis of this ester, right? We have, this is the acid part, right? We get the CO, the C double bond O comes from the acid. That would give you a 3-carbon acid. That would be propanoic acid. And then oxidation of propan 1-ol, again, this is a 3-carbon alcohol. That would give you a 3-carbon acid as well. So that would also give you propanoic acid. So the answer is A. Which ester may be hydrolyzed to produce 2 products, one of which may be reduced to the other? So they're saying when we hydrolyze this ester, we get 2 different products, and one of those products can be made from the other products by reduction. We can reduce one of those products to make the other product. Now, in the case of A, we have this CH3CH2COO. Again, the CH3CH2CO, this 3 carbons comes from the acid, this 1 carbon comes from an alcohol. So we have 3 carbon, 1 carbon, so that would be propanoic acid and methanol. That would be propanoic acid and methanol, right? Obviously, you can't reduce propanoic acid to give you methanol. You can't reduce propanoic acid to give you methanol, so it can't be A. In the case of B, we have this guy over here. We have the CH3CH, CH3CO2. So let's draw that out. We have a 1, 2, 3 carbon chain for the acid and a methyl group in the branch. So we have 1, 2, 3. That's OH. So we have CH3 and then a C, CH3C, and then we have a CO2, right? The CO2 comes from the acid, the C double bond O, and then we have a CH3 in the middle, right? So that's this guy. And the alcohol, okay, if we break apart this ester linkage, we have CH3 twice, CH, and then the CH2OH, right? CH3 twice, CH, CH2OH. So we have 2 CH3s bonded to the same carbon, right? We have 2 CH3s bonded to the CH, 2 CH3s bonded to the CH, which is bonded to a CH2, which is bonded to an OH. And we know that this guy, right, this guy can be reduced to make this guy, right? Because we know that carboxylic acid can be reduced to a primary alcohol. They have the same carbon chain. So here we have 2 different products, and one of those products can be reduced to make the other product. For reduction of carboxylic acid, we have to use anhydrous lithium aluminum hydride. Remember, NaBH4 does not work for reduction of carboxylic acid. It is not a strong enough reducing agent. So the answer over here is B. 2 compounds X and Y are mixed and a little concentrated sulfuric acid is added. Okay, a little concentrated sulfuric acid. This is a hint that the sulfuric acid is being used as a catalyst. Okay, this is a hint that the sulfuric acid is being used as a catalyst. Ester Z is found in the resulting mixture of products. Ester Z is found in the resulting mixture of products. Which two compounds could be X and Y? So we know concentrated sulfuric acid is a catalyst for esterification. So that means that we have an alcohol and a carboxylic acid group reacting, right? Now, if you notice, right, when you look at ester Z, right, when you look at ester Z, you have a triester, right? This is an ester linkage, this is an ester linkage, and this is an ester linkage, right? But what you can see here is that there's no possibility of ethanol, right? There's no possibility of ethanol here. The reason why is because um, if you were to hydrolyze any of these linkages, it wouldn't produce ethanol, right? So we know that it can't be ethanol, right? Now, as far as the carboxylic acid is concerned, right, we can have ethanoic acid here, right? So ethanoic acid could result in the formation of this ester. Why? Because this guy and this part over here, right? Again, remember the C double bond O comes from the carboxylic acid. So we can have this CH3 and then this CO coming from an acid. So CH3 COOH. So it has to be C or D, right? And when you get rid of these two, right, what are you left with? One of the reactants is obviously ethanoic acid, and then this guy over here, right, would be your other reactant. This guy over here would be your other reactant. So what is that? Well, that's an OH, right? This would be an OH over here. This would be an OH over here, right? So this is also an OH. Then we have this, we have this, we have an O bonded to a C double bond O, and then we have this and then this, right? So what is the structural formula for this guy? Well, if you try to figure out the structural formula here, it would be a lot more complicated. But the key idea here is that you have a CH2OH group. Okay, you have a CH2OH group and you have an ester linkage, right? You have a CH2OH group and you have an ester linkage. So if you look at these two products, right, it's only C that has this ester linkage and it has these two OH groups, right? We have the CHOH, we have the CHOH here, and we have the CH2OH, right? We have the CH2OH, we have the CHOH, and we have this ester linkage. So the answer has to be C, okay? This compound will react with ethanoic acid, which is the other reactant, and we're going to get ester linkages on these two alcohol groups to give us the final product, which is ester Z. The diagram shows a section of a polymer molecule. Which monomer will produce this polymer? Now over here they've given us a section of the polymer. We know that when alkenes undergo polymerization, right, the addition polymers are saturated. They don't have any double bonds. So if you have one double bond to begin with, the polymer will have 0 double bonds. Here the polymer has double bonds. Which means that the initial monomer will have more than one double bond, right? It would have more than one double bond. So in this case, the only possible answer is B, because it has two double bonds, and when this guy polymerizes, the repeat unit will have one double bond. Okay, the repeat unit, which is this guy, this is the repeating pattern, right? The repeat unit will have one double bond. Okay, so the answer is D. This is polymerization of conjugated dienes, where we have alternating double bonds. By that I mean we have a double, single, and then a double bond, and then the repeat unit, the double bond is in the middle. So the repeat unit, the double bond is in the middle. Okay. There are two naturally occurring isotopes of bromine. One isotope has 44 neutrons, the other isotope has 46 neutrons. Ignoring fragments, how many peaks are there in the mass spectrum of tribromomethane? Now, bromine has an atomic number of 35. Okay, bromine has an atomic number of 35. So we have two possible isotopes. We have either bromine 79 or bromine 81, right? And in this compound, we have three bromines. Right? Now, if we have three bromines, right, they could all be 79. Okay, they could all be 79, right? We don't have to consider the carbons and the hydrogens because they've said that we're only going to have carbon 12 and only hydrogen 1. So we only have to think about bromines. The three bromines could be 379s, okay? They're going to add up to 237. we could have 181 and then 279s, right? We could have 181 and 279s. Doesn't matter where the 81s are, right? Because in this case, we're not really concerned with abundance. We only care about the possible masses. That would have a mass of 239, okay? We're only looking at the masses of the bromines, right? Because the mass of carbon and hydrogen are fixed, right? We could have two 81s, okay? So we could have 81, 81, and 79, in which case that would be 241, or they could all be 81s, in which case the three bromines would have a mass of 243. So we have basically four different possible masses, right? We have four different possible masses depending on the number of bromine 79s and 81s we have. So the answer is C.